and welcome back. This is Federico. Today I will be continuing the series on our deep learning library, which I've decided to baptize as Deep Feds. So today it's actually a very exciting episode because I've done a bit, not a lot, but I think this means that our library is finally ready to be kind of deployed on MNIST, and then I'll be showing you how to actually create like a web API to deploy libraries. And then training in on MNIST, which is quite a simple data set. But yeah, so today I'll be going over what I did, which was I implemented the ReLU activation layer, and then I also implemented the Adam optimizer. So quite some stuff. And I also changed the API of the library. So now, as you can see, the API just takes a constructor, which has some parameters, which I'll go over, and then it has this fit method, which is very similar to Scikit-learn, and this predict method, which again should remind you of the Scikit-learn API. Okay, so this predict method is just simply calling this forward method, so that's just kind of a rename. I didn't rename this directly because this was being called all over the place, and I just thought this would be cleaner. And also this is consistent with the layer API, so I think it's just nicer like this. So this fit method used to be in its own train file, but now instead it's a part of this neural network class. And it does the same thing, but I guess also I moved the optimizer step inside this class, and then this actually goes and dispatches the call to the actual optimizer classes. So I think this is kind of a slightly improved architecture of the library. And yeah, so first I'd like to talk about these hidden layer sizes, which now becomes a tuple instead of like the old way, which maybe I can show you here. So the old way would be to do it like this, where you'd kind of create a sequence, or a list in this case, of linear and activation layers and stuff. Now this is what it looks like, the equivalent idea, which I think is much kind of more readable, right? So for example, in this scenario, this is a hidden layer with 10 neurons, and then the input size of the network is 2 and the output size is 2. So you can imagine I don't have my drawing board out, but you can imagine the network with 2 input layers, 10 hidden layer, or 10 neurons in a hidden layer, and then 2 neurons in the input, 10 neurons in the only hidden, and then 2 neurons in the output, right? So this is what it's saying, and then the activation, if we want to swap it out, we can just swap it out with ReLU, for example, if we want. And then if we run this, it will obviously do its thing and converge, and yeah. Now the way this was done is it will first, so pretty much this initialization takes this activation layer, it takes input size, output size, and hidden layer sizes, and then it kind of concatenates this as tuples, so we get this one big tuple. In this case, it would be 2, 10, 2, right? And then this one we can actually use to create the sequence. So in this case, we would get like linear. We want a list of linear 2, 10. We then want this activation function, and then we want a linear 10, 2. And here there's no activation because this is the last one. So this is what we want to construct from this, and the way we do it. The way we do it is through this function called construct layers. This construct layers function is here, and pretty much it does exactly that algorithm. So it will loop and then figure out the sizes for the linear layers, and then it won't append for the last layer. So this is kind of how it works, right? And yeah, so maybe let's look at the more interesting thing, which is this Adam optimizer. Maybe I can clean up this code. So this Adam optimizer is inspired by this algorithm here in the Adam paper from 2017. So this is exactly what I'm doing. Just followed it obviously line by line, and it also suggests values for these parameters, which are actually these ones here. So I just took their suggested values, and obviously they know better than me what to put for these values. So it takes this step size parameter, it takes these 2 decay rates, it takes obviously the objective function, but I guess we just care about the gradient, so we just give it the gradients, and then it has these m and v vectors and this time step which we initialize, and then until convergence. So in our case, convergence just means the number of epochs we want to run it for. It will increase the time step, collect the gradients. It will then update this m vector through this rule. So it's like this update is in a function of beta 1 and the gradients, and then this v vector is in a function of beta 2 and the gradient again, and then it takes this correction for the actual update. So this correction factor is just like a normalization, right? And it's a function of the time step. So as this time step increases, it will actually lower the step this takes, and then we actually update the gradients, and then we loop through it, right? And that's exactly what we're doing. So first we want to kind of collect the dimension of the gradients which we will have, because or else it won't know this, like NumPy will complain, right? So this is why we have this split here. It could have probably been done better, but I just didn't think it was worth it. So in stochastic gradient descent, it'll just use the old code. If it's Adam, then it will actually run this code, which sets the dimensions and then collects. So it kind of uses a list comprehension instead of a generator, because we need all of the gradients, because the shapes are not the same, if that makes sense. I mean, it might not make too much sense, but if you actually go to implement it, you'll realize that either you kind of dispatch a bunch of Adam optimizers for each layer, or you just do it this way, which is much simpler. So, I mean, I guess it's just, maybe not simpler, but it's just the way I decided to do it. And then we're doing exactly that. So for each kind of gradient and m batch, we are actually updating it with what the paper says, and then we're calculating our m hats and v hats, and then actually going in and updating the parameters. And as you can see, if we have it's converging quite nicely, and then what we can do is so here's using stochastic gradient descent. Adam seems to not work as well for this problem, but it still converges, as you can see. Maybe you need to mess with the learning rate and stuff along those lines. But actually, if we go into this FizzBuzz example, I tried it with Adam. This is the default learning rate, so we can actually just get rid of that. And no mod me. Oh yeah, right, because I removed that. And then as you can see, the loss function is kind of going lower and lower. I mean, it's still jumping up and down, because obviously this is a much harder gradient space than the XOR example. So as you can see, while we let this work, we can look at the different kind of parameters we can have. So in inputs, in the constructor, we can obviously have the hidden layer, input size, and activation functions. And then we have in the fit method, we can choose a number of epochs, the batch iterator, the loss function, the optimizer, and stuff like that. One last thing, maybe I can mention the layers. I actually added ReLU, and this is a very nice branchless way of doing ReLU. So if we just go through it, ReLU is the rule of so if x is positive, then we return x, and then else we return 0, right? So this is pretty much what ReLU does in pseudocode almost. And so obviously we can make it much neater, right? And this is kind of this branchless idea where if x is positive, this will be true or 1, and then so it will just return x. If x is negative, this will be 0, so it will return 0. Similarly for the derivative, we want 1 for positive and 0 for negative. So if this is positive, it will return 1. If this is negative, it will return 0, because this will be 0 when it's negative. So this is just a neat way of implementing ReLU, I thought. And yeah, so as you can see, Adam solved FizzBuzz perfectly, which is quite exciting, which means the implementation is correct. and then we can fizzbuzz. We can try with ReLU, with ReLU, with SGD, and then we can see if this. Whoops. Okay, well, SGD, maybe there's something wrong with it. Does it? Maybe the learning rate is too high. I remember with SGD, and let me quit it immediately. Okay, so yeah, with SGD it seems that the gradient is just too high, and it explodes. So with SGD, I guess you have to mess with the learning rate. So maybe something a smaller learning rate. And yeah, okay. So with a smaller learning rate, it can work. But as you can see, Adam kind of just works out of the box, and I think this is the advantage of Adam. That Adam will would just kind of pretty much work for most landscapes, while SGD will need some more tweaking on the learning rate. So yeah, hopefully you enjoyed this video. Hopefully you learned something about Adam and this stuff. And yeah, see you next time, hopefully. Bye bye.